Okay, so sort of like we were doing at the end of dynamics, I want to just walk through some of these derivations today. Have you walk through them. So let's start with, so we're going back to column buckling. And we're going to work on these derivations, and there are two different directions that that you go with these. Sort of two fundamentally different starts. The first one is if the column is pinned at the base. This is simpler. And the second one is fixed at the base. In both cases, we're going to start out by isolating just a piece of the beam. So we're going to start by isolating a piece of the column. From 0 to some arbitrary point x, okay? So let's start with pinned at the base. That's the simpler one. In that case, there's not going to be any reaction couple at the ground, okay? The reaction couple is what complicates things, okay? So we'll start with pinned at the base. That means there's no reaction couple at the ground. At the base. So start out with a free body diagram of the piece of beam, and then go to the moment equation, the rotational version of Newton's second law, okay? So see if you, so the free body diagram I usually draw for this is just the shape that I happen to know it's going to take in the end. But we don't know the angle of the column at the base. That can be any angle because of the pin. We do know that whatever compressive load is being applied from the top, that's also the internal load at x. And that's also the reaction load at the ground. So both of these are going to be P. This is the deflection V. And we're going to take the moment about the base. And so the moment equation says, oh, and I forgot the bending moment. So remember that since this is just x, okay, that's not the top of the beam. At the top of the part that I've drawn, there's a bending moment because that's, that's connected to more beam. You know what I mean? This isn't going all the way to L. It's only going to some arbitrary x. So we're going to have this bending moment M. The force P at the base acts right through the about point, so that one doesn't produce a moment, but we do have M plus this moment of P times V is equal to 0. Next, we're going to use what we know about elastic beams. So this is a relationship between the internal bending moment at a given x and the deflection. And from this, you're going to derive the governing differential equation for pinned at the base. Okay, so what we know is that at a given x, E, I, V double prime is equal to M. So now we can substitute that in here, and we have E, I, V double prime plus PV is equal to 0. I usually put it in the form with the leading term having a coefficient of 1. So divide everything by EI. You got V double prime plus P over EI times V is equal to 0. And that looks a lot like the undamped oscillator problem. You just have a different coefficient on your function. So now, assume that this has a sinusoidal solution. And use the boundary condition at the base to update your equation. Okay, so we're going to assume that this deflection has the form C1 times cosine of, and I mean, this is really the same exact logic as the oscillator. What do we want the argument for these sinusoidal functions to be?
Square root pi over v.
Yep. It's x, not t in this case, but and then plus C2 times the sine with the same argument. So the question?
I have the numerator and the denominator. Must have messed up. For the governing equation, can you scroll up a little bit?
Mm-hmm. So EIV double prime goes in place of M, and then divide everything by EI.
Okay.
Okay, so now the one boundary condition we're going to use is we're going to use what's happening at the base. And since this is pinned, the only boundary condition we have is that the deflection at x equals 0 is 0. And so plug in x equals 0 and you get that C1 times the cosine of 0, which is 1, plus C2 times the sine of 0, which is 0, is equal to 0. And so C1 is equal to 0. And now we'll update that function. And you get that v of x is equal to C2 times the sine of square root of p over EI times x. So that's the updated solution before, so updated solution before we start using the boundary conditions away from x equals 0. Before we use the boundary conditions away from the base. Okay, well, now let's do the two boundary conditions that, so our step 4 is we're going to use the boundary conditions away from the base. And that's different on the different cases. We've talked about two cases here. One is where it's only pinned at the top, and one where it's pinned at the middle. And then you could do it anywhere else between the base and the top. But so let's start with first, we're going to assume that it's pinned at the top. Okay, so think about what's required for that to hold and see if you can come up with the critical p-value for pinned at the top. Okay, so now we're going to say that the deflection at x equals L is equal to 0. And so V at L is equal to C2 times the sine of square root of P over EI times L, and that's equal to 0. Well, now we don't want to set C2 equals 0. That's one solution, but it's trivial. So we're going to look for non-trivial solutions. And the non-trivial solutions are where sine is equal to 0. So what values of the arguments make sine equal to 0? So we can say this is equal to 0 at square root of P over EI times L equal to, this would be n pi, where n equals 0, 1, 2, so on. Okay. If we use the n equals 0, we're going to get that the critical p-value is 0. That still meets the boundary condition requirement, but that's not a solution that we want. That just means that the thing isn't isn't being loaded at all. So for our critical p-value, we want this. This is the first non-trivial solution. So take the square of both sides. We have p over ei times L squared is equal to, all right, this is 1 squared times pi squared. Solve for p, and you get that the critical p-value is equal to ei pi squared over L squared. Any questions about that? Okay, for the pinned case at the base, the only other boundary condition we used away from the base was that at the middle of the beam at L over 2, it was also pinned. So let's do that. So now for B, we're going to do pinned at L over 2. And the reasoning, the process is going to go exactly the same as it did in part A. We're just using L over 2 instead. So see if you can come up with the critical p-value for that. Okay, so we're starting with our expression, our updated expression for V. And we're saying V at L over 2 is equal to 0. And so V at L over 2 is equal to C2 times the sine of the square root of P over EI times L over 2. And we're setting that equal to 0. By the same logic as before, that sine term, that sine factor is equal to 0 when square root of P over EI times L over 2 is equal to n pi for n equals 0, 1, 2, 3. And again, we want the lowest non-trivial solution, so we're going to take n equals 1. Square both sides, we get P over EI times L squared over 4 is equal to 1 squared times pi squared. And so P critical is equal to 4EI pi squared over L squared. Anybody have any questions about that? Okay, so that's all we have to worry about for the case of pinned at the base. So now let's think about the case where it's fixed at the base. Well, this time, because it's a fixed joint, we are going to have an external couple applied at the base. Let's call that M sub 0. So the first step is draw a free body diagram. From the base to some value x. and use the moment equation. Okay, so that's the first step. Okay, so in this case, I'm going to draw sort of the shape that it's going to take. It's going to start out vertical because of the fixed joint, and then it'll deflect later. And we still have these compressive forces P. We still have the bending moment M at our position X. And the thing that's new is now that there's a fixed joint between the ground and the base of this column, we also have a couple M sub 0 applied at the base. Okay, and if the about point is going to be here again, then the moment equation says M sub 0, that's a terrible M, yes, M sub 0 plus M plus, this works the same as it did before, this is V, so plus P times V is equal to 0.
Could you model this with the assumed deflection being the other way, and then you'd have a negative PV?
Yeah, you'd have to, you cannot do that because of the elastic beam relationship defines the direction there. The moment in this equation implies like a right-hand rule, which implies a coordinate system. Okay, so that tells you, the right-hand rule in a roundabout way tells you the direction a positive deflection has to be. Since our x is going up. Yeah. Okay, so now we're here. The next step is use the elastic beam relationship to derive the governing ordinary differential equation. Okay, so, well, the elastic beam relationship says, okay, so first of all, it says E I V double prime is equal to M. The key thing to remember is this only holds for internal bending moments, okay? It doesn't hold for reaction moments, reaction couples. So this, you can't replace the M sub 0 with this. You can only replace the M with this. And so we have M sub 0 plus E I V double prime plus P V is equal to 0. Rearrange this and you get V double prime plus P over EI times V is equal to negative M sub 0 over EI. So that's the governing ordinary differential equation for fixed at the bottom, at the base I've been calling it. Okay, so now how are we going to go about solving this? This is where it gets a little different than the first case. So now we're going to find a general solution to the homogeneous equation That's the equation that says, so we're just getting rid of anything that doesn't have a v or a derivative of v in it. So the homogeneous equation is v double prime plus p over ei v is equal to 0. It's easy to come up with a solution to that, a general solution to that, okay? And then we also have to find any one solution to the full equation. And add those together. And that gives you the general solution for the full equation. Okay, so I guess this is the last one we'll do. I guess let me just keep going through it. So think for a second, though, if you have any idea where to go with all this stuff. Okay, so for the homogeneous equation, we're just dealing with this equation here. And so the solution is going to be that v as a function of x is equal to some c1 times the cosine of square root of p over ei times x plus c2 times the sine of square root of p over ei times x. And that gives you every possible solution to that homogeneous differential equation, okay? It doesn't give you any solutions to the full equation, okay? Because if you took the second derivative of this and added it to p over ei times v, it would give you 0. It wouldn't give you negative m sub 0 over ei. But now for the full equation, notice that if v is a constant, then v double prime is 0. Okay? So we're going to assume that v is a constant, and we have the full equation says v double prime plus p over ei times v is equal to negative m sub 0 over ei. Okay? If we're assuming that v is constant, then this is just 0. We don't have to worry about it. And now we can just solve for v. And so we get that v is equal to negative m sub 0 over p. And so now the general solution to the full equation is that v is equal to c1 times the cosine of square root of p over ei x plus c2 times the sine of square root of p over ei times x minus m sub 0 over p. Okay, and now we're ready to go to the boundary conditions. Yep.
Quick question on M naught. So as M naught increases, what does that means we have less bending moment?
It just means based on the shape of the beam. I mean, this beam, I drew it in one orientation, but this could wiggle all over the place, you know. So it just means that, you know, the reaction load required to keep that thing in equilibrium is changing. We just have to take it into account.
Yeah, I'm just wondering how, like, if you had a material that had a really big M naught value, you'd be less prone to buckling.
Oh, I gotcha. Well,
like we can assume that geometrically, and then can we see that appear in any of the modeling we've done?
that is not connected to the material. It's just connected to the shape of the beam. And we're just trying to find, and we're just imagining this in a single static position where all of those external loads are constant, the P is constant. And so we're just assuming that M for the load that we're applying, that's going to end up being our critical load, we're just assuming that that M sub 0 is some fixed thing that we could know, but we don't. And it doesn't have anything to do with the material. It just has to do with the shape of the beam and the P value. Okay, anyways, that's all. All right, I don't want to spend forever doing this stuff, but we'll do a little more of this on Wednesday, finish with the boundary conditions, and then we'll move on. Okay, that's it.
We want to like